Okay, the point with zero electric field will definitely not be somewhere between the charges because no matter what, it's going to go to the right. It's going to repel from the red one and attract the blue one. So there's not going to be any answer in there. There will not be any answers anywhere over here. Like nowhere over here will it work because it's going to repel from the positive 3. It will attract a little bit to the negative 1, but it's the repulsion is definitely going to be a lot stronger than the attraction for 2 reasons, because the charge is bigger in size and also because the distance is a lot closer. So there's not going to be a solution on the left side. So if there's any solution, it's going to be somewhere over here on the right side, because it's going to attract towards the blue but repel away from the red. And there's a chance they will balance because the blue's got the advantage of the distance, the red's got the advantage of the charge magnitude. Now, my intuition tells me it's going to be somewhere a bit more, not that close to the blue one. Maybe not even. It's probably going to be somewhere over here. Again, that's just my intuition. I'm going to just check for sure with the calculations. So we're given that the distance between these two is 1 unit. And we're given, well, I'm going to call from the blue charge to P, I'm going to call that X. So again, there's a brute force method and there's a more deeper logical thinking method. So starting with the brute force method, I'm just going to set the 2 electric fields equal to each other. The electric field created by the red equals the electric field created by the blue in magnitude. I've already analyzed the direction when I was analyzing where could there possibly be a solution. So since I've already done that work, now I can just focus on the magnitudes. So I'll just use the electric field formula. So the red one will be called charge 1. The blue one will be called charge 2. So the electric field at point P created by charge 1 will be K times 3Q over the distance squared. The distance is going to be X plus 1. That's the total distance from charge 1 to point P. And that's got to equal the electric field magnitude created by charge 2, which will be KQ over X squared. And then K's cancel, Q's cancel. We have cross multiplication and simplification. So we'll have 3x squared equals brackets x plus 1 squared. Got to solve this quadratic. So I'll expand out the one on the right, bring everything to one side. So I'll bring everything to the left side. Not factorable. So quadratic formula. So 2 plus or minus root 12 over 2. So 2 plus or minus 2 root 3 over 2, 1 plus or minus root 3. It's not going to be negative. The negative's inadmissible. So x will equal to 1 plus root 3 units. So my intuition was a bit wrong. I think it's got to be more than 1. It's got to be more than 2. It's way over here. Yeah, 1 plus root 3, that's like 2 point something. Okay. I'll just leave it like that. So that's kind of the brute force way. The shorter way, I wrote it out a bit more in full for the previous example. I don't think I'll do that this time, but you may realize that in terms of ratios, x over 1 plus x will have to have a ratio of 1 over root 3. Yeah, so in terms of distance, the blue one needs to be closer by a ratio of 1 over root 3 to balance out the fact that this charge is 3 times as much. And that should work out to the same thing. So this still requires some cross multiplication, some is it the same thing? Root 3x minus x equals 1. Common factor, root 3 minus 1, x equals 1. Divide, x equals 1 over root 3 minus 1. Is that the same thing, 1 over root 3 minus 1? Well, I'll have to rationalize the denominator here. No. Oh, okay, I messed up. I messed up the first one. This is probably the right answer. I messed up the first one because in my quadratic formula, it's over 2a. It's over 2a, so it should be over 2 times 2. And that's where that 2 went. Okay, good thing I did it the other way to double check that.